let's look at the big alternate definition of e to the z. This is going back to problem 8 in the part 2 PDF. And that is that we're going to define e to the z by exactly the same power series that you can use to define e to the z for a real number. So if you've had the usual high school or beginning calculus, beginning college calculus treatment of power series, you probably think they're really weird and scary because they emphasize some of the technicalities of them way too early. This is just an overgrown polynomial, and it's going to behave exactly like a polynomial. It just doesn't stop. Now, there are definitely subtleties to power series that can get things really weird. They don't come up here. This is one of the nicest power series ever. It's going to behave a lot like a polynomial that just doesn't happen to stop. Okay. In particular, the derivative of this is exactly what you'd think it would be: differentiate term by term, and that's going to be very interesting if you take the derivative of that. And the algebra, adding these guys, multiplying them, nothing can go wrong with this power series. Not to say it can't go wrong with other power series, but this one is beautiful. So if we just trust that, then it's not really going to be hard. Okay. One thing that's a good reason to emphasize this one, perhaps, over this definition, even though this is wonderfully geometric, power series have a very, very special place in complex analysis when you get into honest-to-God complex analysis, not just the very basics of the stuff that we're doing right now. And so this is what almost anybody working at complex analysis would use as their definition of the exponential function. It's going to be the most common definition you'll ever see when z is complex, certainly. Okay, so let's look at some questions we want to know about this. And I'm just going to pretty much just write down the questions that are on the PDF and not really do them. Does this imply, this was supposed to be our proposed solution, does that imply that y prime equals iy? That is not hard to do. You can either do it, if you're pretty good with summation notation, you can do it right here, or you can just write this out, this many terms, with an it everywhere, take the derivative, you'll see that it works. Okay. And so that's a big deal. This is the first place where we link the algebra of complex numbers with the i's to the calculus and start to believe, hey, there is such a thing as something when you differentiate it, you get an I coming out. Okay. But what's really, of course, interesting, where this really came up was if this was our guess, in fact, both of these guys, plus or minus it and the exponent, that was our guess as to something that satisfied this differential equation that doesn't mention I in the equation, and yet we seem to be forced to define something like this to get a solution that looked like an exponential. Okay. Again, not hard. Take two derivatives of this guy, just as if it were a polynomial. Follow the usual rules for algebra, including rules of algebra for I. Okay, let's see. If I have e to the alpha t, okay, and alpha squared is lambda, which happens to be negative, the claim is that y double prime is indeed equal lambda y. Okay, and that's just an easy generalization of this guy. Okay, and okay, oh, and of course this is plus or minus, because if you take two derivatives, the chain rule should basically give you alpha squared regardless of what you get. Okay, you can check all that from here, or if you just believe the chain rule works in the usual way, it depends on how cavalier you want to be. That would be another way to show it. So I'm doing this kind of quickly because it's nothing hard about it, but this is really key stuff. Okay, let's see, we're up to D here, I think now. Okay, if I've found some alpha whose square is lambda, which is a negative number, okay, which is the new thing we're able to do now with complex numbers, and y of t is a combination of that guy and the exponential with minus alpha t, then we should still satisfy our fundamental equation. Okay, that's good. Alrighty, so at least we have some sort of solution. Now it's using complex exponentials, it's using complex numbers. This is not a real solution as yet, to this problem that only used real numbers. But it's a huge breakthrough because it looks exactly like the solution we had when lambda was a positive number. It's a combination of exponentials. Okay, and this does seem to start looking like it works. And of course, what do we really care about? If the claim was if we found a number that satisfied this algebraic equation, and y of t is defined to be e to the alpha t, then the claim is that that y satisfies this differential equation. And of course, there's going to be two solutions here, and each of the alphas is going to produce one of these guys, and so you're going to get two independent solutions. Okay. So let me see if I can squeeze that in here. So let's say alpha 1 and alpha 2, right? And there's a lot more we could do at this point. If we were doing real differential equations class, this is getting close to the point where we'd start really practicing this in detail and looking at lots of different alphas. We're going to focus on just a few because the idea is just why would you do complex numbers? And we're really getting to the point, very close to the point where we can see, yeah, this is really making sense. Okay, so that's going to be the general solution if we allow complex exponentials to this problem. Now, there's still an issue of, wait a minute, this is like y is like the position of a mass on a spring. I shouldn't get complex positions for that. The key is going to be, and I'm not sure how much of this I'm going to do. Good thing to look in a differential equations book for if you really want the details. The key is you can choose C1 and C2 to be complex in a clever way so that this whole thing actually comes out to be real. Okay, so we're in a good position here. We've got a very explicit definition of e to the x, or e to the z, and at least for these kinds of, the special case of that, where alpha is a solution to a quadratic, it seems to be starting to solve our problem with the only worry that we seem to be getting a complex solution. Okay, so that's what number 9 starts to address. Okay, so let's go back. Let's backpedal one more time to just this one. This is pure harmonic motion, no damping. But it was the place we got stuck before we invented complex numbers. So let's go back to this. It's reasonable. Okay. And we now have two different solutions for this. Okay. Let's say if alpha squared is equal to lambda, so in other words, alpha is just some square root of lambda, complex number, then we've got y equals c1 e to the alpha t plus c2 e to the minus alpha t. Because here, for this kind of equation, it's just plus or minus. There's not a complicated relationship between the two roots. Okay, but we also have y equals, let's say, a cosine, omega is a good letter for this, plus b sine omega t, where omega squared is minus lambda. So this is what I was calling, so omega is what I was denoting as root minus lambda before. It's just kind of ugly to keep doing that. Okay, so the question is, how can these possibly be the same? Okay, well, we've already got a very strong hint that this alpha here, this is going to be a pure imaginary number. It's going to be something times I. In fact, it's going to be omega I. Why don't you prove that? If this is true about omega, where lambda is a negative number, so omega is actually a honest to God real number, and you take omega I and you square it, you'll get lambda. It's not hard. Okay. So this is a pure imaginary number, so e to a pure imaginary, it's basically this sort of e to the it thing. And we were just talking, when we did problem 10 a little in advance, we were talking about how we've got this strong suspicion that that just goes around in a circle. Circles have to do with cosines and sines. Okay, so we already had a big hint of that, but now it's time to really make sure it works. Okay, so what's special about a circle? It's about the magnitude, right? Okay, so this is where we go back to the magnitude thing. And we've got, I want to remind you, there's this wonderful connection of magnitudes and bars, the complex conjugate. And so whenever you're thinking of magnitude of a complex number, don't forget to think, hey, the smart way might be to first think about how bars work. Okay, so that's what problem part A is about. The claim is that e to the z all bar is the same as e to the z bar for any complex number z, not just it or anything like that. Okay, I'm going to let you do that. Okay, it's from the power series definition. It's the easiest way to do that. Literally just write it down. And again, it depends on whether you want to try to do it slickly with the summation or just write out the first two terms and then believe the whole thing works. Okay, so what do we really care about right now most? It is the e to the it. Okay, so I'll do this one. It's pretty easy. Just think about that. E to the it bar, if this is true, that's e to the it bar. Now t is a real number. This is pure imaginary. So this is just e to the minus it. Okay, so when you bar an e to the it, it's the same thing as e to the minus it. Okay, so why would that be useful? Ooh, it might be useful because of this. Interesting. Okay, so let's take e to the it times e to the it bar. Oh, you know what? I think I might have done this in a little bit the wrong order. I forgot. I think yeah, well, unless you'll have to take one thing on faith for a little bit. Okay. Let's use this. This is e to the it, e to the minus it. What should that really be? It should be e to the it minus it equals 1. Now, here's where I think I have things a little bit in the wrong order. Does the sum rule work? Or the product, when you take the product of two complex exponentials, is it really true that this wonderful rule works? Absolutely, and it's super, super, super important. And actually, because it's a little, it's deep enough so that it's not super easy to show. It's not hard. I was actually going to skip it. It's in the PDF as number, what was it in? Number 10 or something like that. And let me just go ahead and say, this is indeed a true fact. It's a little weird to make it seem this is so important. This is so wonderful that this is still true, even though the e to the z is in some ways a much more complicated, interesting object than it was before. Still a wonderful, 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 wonderful fact. Okay, let's make it a tiny bit plausible anyway. We can at least make it very plausible in this case. We have this suspicion that e to the it rotates by an angle t. This would rotate by an angle minus t. What happens if you rotate by it, by an angle t, and then rotate back? You get to where you started. In other words, you're multiplying by 1. Now, it's a little bit circular if you think of that as an actual proof, because we actually are still in the process of being really, really sure that e to the it really does rotate around a circle. But it makes it plausible that, yes, this is really going to work, even if though we bring in these rotations as well as the scaling effect that e to the x has when it's a real number. Okay, so I suggest 3 methods of proving this in the PDF. So let's run with that. Okay, so let's go back to why this was interesting. Why the heck was this interesting? Oh, this was the magnitude of e to the it. Boom. This says e to the it is a unit complex number. It lives on the unit circle. That is a big deal. So it's traversing the circle, and then the only question is, does it traverse the circle in the way we think it does, progressive, uniform speed motion? And we can totally do that, because what do we know about? We know about the derivative of e to the it. Okay, so let's look at, I'm going to use the notation that Stewart's multivariable calculus book uses. So this is just getting into BC calc, a tiny bit of multivariable calc, thinking of parametrized curves. Okay, it looks like, so e to the 0 equals 1. Looks like it's there, and then it looks like it's going in this direction, hopefully. We can check that. And I'd like to say that it actually travels around the unit circle in a beautiful, simple way. Okay. And in particular, I'd like to show that the magnitude of its velocity vector is equal to 1. Okay, so why don't you try and do that? It's a good place to pause. Okay. of course, the magnitude of this guy, the r prime, is I e to the it. And so the magnitude is magnitude of I times magnitude of the it. We just showed that that was 1, and that's magnitude 1, so the whole thing is magnitude 1. So this starts here and is a unit speed parameterization of the circle. That's the most beautiful thing ever. Now, are the arrows really going it this way? Well, let's see. Let's look at r prime of 0 to make sure. Is it going up or going down? And that ascertains whether it's going counterclockwise or clockwise. Well, r prime of 0 is just I. Oh yeah, that's going this way. So with a very little effort, just this much, and then just taking the magnitude, we have got a very nice fact. And so this is a nice, I think it's a nice blend between the calculus, a little bit of different differentiability, differentiation, some algebra, getting a wonderful geometric result. So that tells us we can be very explicit about that. Let's see. If we're going around at speed 1, let's just make that really clear. If we're parametrizing the circle at speed 1, then suppose I'm at e to the it, what angle is this in radians? Think about that. Okay, think about the definition of radians. Well, how much arc length has been subtended? If I went for time t at speed 1, that's arc length t, so that's t radians. So this is the point in the plane at t radians on the unit circle. Or in other words, you should know what I'm, hopefully you can expect what I'm going to write down here. Euler's famous formula for e to the it. Okay, so this thing boggles a lot of people's minds, and there's various ways to show it, but really all the key of it is E does repeated something. IT means it's going to rotate. Remember, the other definition, the non-power series definition, told us that that was just 1 plus IT over n repeated, repeatedly multiplied. And so it's just ratcheting up here in infinitesimal steps around the circle. So repeated infinitesimal rotation gives you an actual rotation. And what the heck is rotation? It's just cosine plus sine plus I sine, because these are just the x and y coordinates, the horizontal vertical coordinates on the circle. Okay, so this, I know it took a while for us to lead up to this, but it really isn't that weird that this is a true fact. Okay, and then of course we get wonderful facts like e to the pi, just plug it in, it's minus 1. Or just say, what does this say? Repeated rotation that goes halfway around the circle gets you to halfway around the circle. This is 1, this is halfway around the circle. Repeated rotation halfway around the circle gets you halfway around the circle. It almost makes it tautological. That's how you know you might have made progress. E to the 2 pi I, that's equal to plus 1. In a way, that's more fundamental, because that's exactly getting back to exactly where you started. Okay, so groovy stuff. Wow, already up to 18 minutes. I think it's probably a good place to stop. Let me see if there's anything else in problem 9. Well, let's finish out problem 9 real quick. Okay, because it's really good. Okay, so if I have z equals a plus bi, okay, that's not necessarily on the unit circle, but we know how to put it on the unit circle or to compare it to something in the unit circle. If that's a plus bi z, then I know I can make it a unit complex by dividing by its magnitude. And now I know those are all of the form e to the it. Well, you know what? If this is an angle, we might as well call it theta. Okay, so any complex number z can be expressed as its magnitude times e to the I theta. That's often expressed just as r e to the I theta, because after all, the magnitude of an arrow coming out of the origin is the same as just the polar coordinate r, the radius, the radial coordinate of that point that's at the tip. And of course, if we want to expand that out, it's just polar form. Okay, this is sometimes called cis theta, cosine I sine. Okay, but this is much nicer, because it tells us, oh, this isn't just some random combination of cosine and sine. When you put these together in exactly this way, you have created the complex exponential for this pure imaginary exponent. And that's pretty awesome. So, all right, that's a good place to stop.